We're going to take a look at Chapter 5, which is focusing on the concept of integers. We're going to look at the meaning of an integer and how they're represented in the number line. And then we're going to look at a few different models for adding and subtracting numbers, as well as the properties. So a set of integers, we use the capital letter I, typically italicized, to include the set. You're going to notice it includes negative numbers, the number 0, and positive numbers, but they have to be whole numbers and not decimals. So we also like to teach our students that they're opposites. -4 is the opposite of +4, just like 3 is the opposite of -3. So if we look at each of these to find the opposite value, we're going to change the sign so that in each one, the opposite value has a change sign except for 0, because 0 has no positive or negative category. It exists outside of those concepts. So one way to look at integer addition is what we're calling the chip model. So you could do this with colored M&Ms, you could do this with money, like quarters versus dimes versus nickels. And what we do is we have one color or one style of manipulative represents one positive integer, and then you have another one that represents a negative integer. And if we line them up together, they will neutralize each other because they're opposites. So here, if I wanted to know -4 plus +3, I would put my 4 red negative dots, I would put my 3 black positive dots, and I'm left with 1 negative dot, which is how I know it's -1. This could even be done with crayons. In the charged field model, instead of putting those dots, we're actually putting the symbols for positive and negative, but we're still lining them up vertically so that we have that neutralization or canceling out factor. The number line model is showing that we're going to move to the left for negative numbers, to the right for positive numbers. So if I wanted to do -3 plus -5, I would go left 3 and then left 5 more. So here's an example of applying this information into problems your students might see. The temperature is -4, and in an hour it rose 10 degrees. What is the new temperature? So to get students to realize -6, we could line up 4 negative, 4 red dots, and 10 black dots. We neutralize and we find that we have 6 dots left. Or we could start at 0 on the number line, go to -4, because -4 is left 4, and then go right 10, which puts us at +6. In a pattern model, it begins with whole number facts, and there's a table of computation. This one is probably one of the more difficult strategies to work with students because it doesn't have that hands-on feeling that the other ones do. So when we're looking at this, we know that 4 plus 3 is 7, 4 plus 2 is 6. Those are our basic math facts. We're going to expand that into negatives and have a whole new set of math facts that have a pattern of counting down. So 3, 2, 1, 0, and so on. Now, the absolute value, this is where Dr. Robinson's going to get on her soapbox. The absolute value does not make a positive number. It doesn't change a negative to a positive. It is finding the distance from 0 to that number. So if you were going and you were driving from one town to another, you would never be told the distance is like -500 miles. You're always given a positive quantity for distance because distance cannot be negative itself. That's why the absolute value has a positive answer, is because it's a distance, not because it just makes something positive. So if we look at the absolute value definition, the absolute value of x would be x for x is greater than or equal to 0. And then if it's less than or equal to 0, it's kind of like you're making a negative negative and you're getting a positive. So here in A, we would just have 20, and B, it would be 5. And again, it's not making it 5, it's measuring that distance. In C, 0 has no sign. In D, so I would have the negative of -3. The absolute value is going to make that 3 positive, but the negative in front keeps it negative. So the final answer is -3. And then in E, we have to do the operation inside of the absolute value. so that we get -3, and the absolute value of -3 is +3. Integer addition has all the properties of whole number addition. So given that we have two numbers that are being added together, that's going to be a unique integer. Our commutative property does exist, and the associative property does exist. The identity property we've also seen exists with integers. So all this is doing is saying the same thing we did with whole numbers exists with integers. Now the additive inverse is what's new here. If I add a number and its opposite, I get 0. So for any integers a and b, x plus a equals b, which also means that b has one unique solution, and I would subtract a from both sides to get it, and that would be b plus -a, or you could write that as b minus a. For any integer, if I take the negative of the negative, it becomes positive. It's like a double negative. If I use a double negative in a sentence, it's really the same as stating a positive statement. So if I'm trying to find the additive inverse of each of the following, I have to do the opposite of them. So the opposite of -3 plus x is simply changing the sign to positive and then keeping that 3 plus x. In part B, I want to take the opposite of each term. So positive a becomes -a, -4 becomes +4. In C, I have the same scenario where I have -3 plus -x. I'm going to take the opposites of those values, and I get 3 plus +x. Now, the chip model can also be used for subtraction. I can do the exact same thing where I'm lining them up and I'm neutralizing them, and then I'm able to group them together. So if I'm looking at 3, that would be 3 black dots. If I'm looking at 3 minus -2, that would be 2 red dots because I have -2. I could also do the same thing if I'm looking at signs, so positive and negative signs could be lined up just like we did with integer addition, or we could do the number line model just like we did, or the pattern model. Those are all the same. We're not changing anything. We're using the same approaches here. Now, there is an extra little tidbit here for the subtraction using missing add-ins. If I want to do subtraction using missing add-ins, then I can actually define this as 3 minus 7. And that way, if I knew 3 minus 7 was some value, then 3 could also be defined as 7 plus that value of n. For subtraction, a minus b is going to be a unique integer, so that a equals b plus n. So if I do 3 minus 10, I'm going to have 3, would be 3 black dots. And minus 10 could be seen the same as -10, so I'm going to have 10 black dots. I would neutralize the ones that I can, and I would get -7. So I could also do this in reverse by thinking of this as 10 plus what is 3? Well, 10 plus -7 is 3. Some students are going to find this more confusing to go and think about subtraction as addition, and so those manipulative models are going to be stronger for that. Here I have -2, so 2 red dots, minus 10, 10 more red dots. I have a total of 12 red dots, so the answer is -12. So subtracting an integer is the same as adding the opposite value. So a minus b is the same as a plus -b. So let's look at that. 2 minus 8 is the same as 2 plus -8. I line my dots up, I get -6. 2 minus -8 would be the same as its opposite, which would be 2 plus -8. We talked about this. When you have two negatives, they become a positive, so it would be 2 plus 8, which is 10. Same thing here. Those two negatives are going to neutralize each other, and I'm going to get -12 plus 5, line them up, and then the same thing here. If I want to rewrite each expression without parentheses, that negative in front of the parentheses means I have to change the sign of everything inside the parentheses. So the b becomes negative, the c becomes positive. And the one below, the b becomes negative, the c becomes negative. because you're only changing what's inside of those parentheses. So let's try doing it with simplifying an expression. Here, I'm going to change the sign of everything in those parentheses so that 5 is negative and x is positive. So that's going to give me negative 3 plus x. That's awkward. We don't like to have a negative number in an expression. So we're going to rewrite that as x minus 3 with a 3 behind the x. We just like to have that x in front. And especially as you're teaching your elementary school students this, let's really work on getting those good habits so when they get to high school, it's just second nature to do that. And then in part B, we're going to do the same thing and change the sign of each one. And we're going to take that x and put it in front. Now the x is negative. So we have negative x plus 8, which is kind of awkward, or 8 minus x. As they move to higher math, we're going to want to see negative x plus 8. So you can teach them to leave it in that format, and that's really going to be a best practice. Here's another example. We're changing the sign of what's in the parentheses, and we know that we have opposites will cancel each other out. So y plus negative y goes away, and I'm left with negative x. So we want you to recall that subtraction is not commutative or associative. It does not have either of those properties. So that means we cannot swap the order and arrive at the same answer. And it has to be done from left to right. The biggest mistake that we see in the order of operations is students don't go left to right. They have to go left to right. So here's an example of just moving left to right. So 2 minus 5 minus 5. First, I have to figure out what is 2 minus 5. 2 minus 5 is negative 3. Then I'm going to have that minus 5 still hanging out because I haven't done anything yet. And that's where I get negative 8. Same thing in B. 3 minus 7 is negative 4. Then I'm going to add the 3 to the negative 4 to get negative 1. In C, the first thing I have to do is get rid of the parentheses. So I would have 3 plus negative 7 plus positive 3. Or I could do 3 minus 4 by completing the operation inside of the parentheses. Either way is right. And that's going to be the lecture on integers.